You mind pulling the door for me? All right. So I'm assuming that it's working properly. I'm not going to really check it. I haven't made any changes. I got my notification, so I haven't really made any changes. If something doesn't work, I'll redo it or create another one or whatever. So today we're going to continue chapter 5. I think last time we pretty much took up the whole time working on the handout, so we did the best that we could with it. It just kind of came out the way it came out, so we had to kind of let that be. But moving forward, we're going to keep moving with chapter 5 with section 5.2, right triangle trigonometry. Just by a quick show of hands, how many people are comfortable with like right triangle trigonometry? What immediately comes to mind when you think of like right triangle trigonometry? Go ahead. Sine, cosine, tangent. You know any like acronyms or abbreviations or anything for right triangle? SOHCAHTOA, right? What does SOHCAHTOA stand for? So the SO stands for what? Opposite over. So in right triangle trigonometry, if we do SOHCAHTOA, the SOH stands for sine is opposite over hypotenuse. So given some angle, sine of that angle is going to be opposite over hypotenuse. The ka in SOHCAHTOA, what does that stand for? So cosine is adjacent over hypotenuse, and then tan is opposite over adjacent, right? So we'll start with a notion of that nature. So some objectives with this section are the following. Find the values of trigonometric functions of acute angles, okay? Use fundamental identities. We're going to get into all of these. Find the values of the remaining trig functions given the value of one of them, and then use the complementary angle theorem, right? So let's look at these. Okay, so we'll start with finding the values of trig functions of acute angles. What do we mean by acute versus what are some of the other types of angles? The straight line, right? Right. So what does acute mean? That the angle is what? Less than 90. What does obtuse mean? And then what's a right angle? What are complementary angles? That's okay. Go ahead. Yeah, that add up to 90 degrees, right? And then what is supplementary angle? Add up to 180. Okay. Let me see if I can do this. So we have our given angle here. Let me see, which is our theta. So again, SOHCAHTOA, sine of that angle is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tan is opposite over adjacent. So you see those listed out in this chart. Again, the way that we remember it is SOHCAHTOA. So now, if we consider sine, where sine is opposite over hypotenuse, what's the reciprocal of sine? What do I mean by reciprocal? If sine is opposite over hypotenuse and we take the reciprocal, what are we doing? Flipping the fraction, right? So what trig function is the reciprocal of sine? What trig function is that? Is it hypotenuse over adjacent? You right there, say it. Oh, it's cosine. No, oh, so close. Not cosine, but okay, so you see in our chart that opposite is B and hypotenuse is C. So then when we flip it, we have C over B. Which trig function is C over B? Cosecant. Cosecant, right? So when we go to flip sine, the reciprocal of sine is cosecant. You actually already have this on Moodle. I don't mind if you take pictures if you want, okay? So it's kind of a little backwards, right? So if we have sine, when we go to take the reciprocal, intuitively we might think, oh, secant goes with sine, but it's actually the reverse. So when we flip sine, the trig function that is the reciprocal of sine is cosecant. So if cosecant is the reciprocal of sine, what's the reciprocal of cosine? Again, keeping in mind that it's reversed. Secant is the reciprocal of cosine, and then what's the reciprocal of tan? Cotan, right? So that's how we use this chart, okay? So again, this is actually already on Moodle. Oh, cool. Yeah, I don't know. That's just, I'm going to let it be. We're going to be exploring. So I've noticed that there are about 3 different ways of approaching a trig question in general. We're introducing it with right triangle trigonometry. Once we branch out from right triangle trigonometry, another approach is we can do a unit circle approach. I have what I feel like is a simplified version of how to use a unit circle. And then the third technique that we have for using trig functions is looking at the graph of trig functions. Like if you imagine a graph of sine function, what kind of image do you get when you think of the graph of a sine function? What am I doing with my hands? A wave pattern, right? So I'm not over here dancing, but I'm like, I mean, a little bit, you know, hey, do something, whatever. but those are the three different main techniques that we have for solving trig functions and trig equations and things of this nature. Sometimes we can use a right triangle trigonometry, and we're introducing it here today. Sometimes this doesn't work. When this doesn't work, then try the unit circle approach. We'll talk about that. That's coming up down the line. If that doesn't work, then we can try looking at the graph of these trig functions, sine, cosine, and tangent, and all that. So we're going to explore these different techniques, again, starting with the right triangle trigonometry. Is this okay? Is this okay? So the first technique we're going to explore, again, are these right triangle trigonometry. So we kind of talked about all this, again, from SOHCAHTOA. And when I'm saying SOHCAHTOA, what I'm referring to, what color are you feeling today? How you feeling? Blue? Okay. Okay, because of the weather? This like blue? Okay, so SOHCAHTOA, what I mean is this. SOHCAHTOA, right? Where the SO stands for sine is opposite over hypotenuse. The CA stands for cosine is adjacent over hypotenuse. And the TOA stands for tangent is opposite over adjacent. So that's what you see listed out here. And then the corresponding reciprocal function or trig identities or whatever they're called. You see them correspond below each one, right? Trig property or whatever. Okay. So let's keep it moving. So let's look at this example. We're asked to find the value of each of the 6 trig functions of the given angle theta, right? So pretty much once we have sine and cosine, the rest just flow naturally, in my opinion. Okay. So let's start off with sine of theta, right? If we're going to do sine of theta, sine stands for what again? Wait a minute. So if we want to actually find the actual value of them, what do we need to find? What are we missing from our triangle? We were missing one of the legs, right? So do we have a way? We have 2 of the 3 legs of a right triangle. Is there a way? Do we have some technique for finding that missing leg? Yeah. Okay. I wasn't sure about this, the following statement. But I overheard a professor the other day saying what I had been feeling all the while, and I never took the time to research it, but apparently, and I don't know if I should be saying this on the record, but I'm going to say it anyway. Like apparently Pythagoras was not the original, person that, he probably like rehashed, how like a lot of stuff is like stolen and like the credit is given to people that didn't really originate the idea. I got a little buzz the other day that kind of thing is going on here as well. Even though we all say Pythagorean theorem, apparently he was not the originator. So if you actually find, if you all can actually find some information on that, legit information, like, not anything that's like, it has to, how to verify when you research and things like that. If you could actually find something that speaks on that, like if Pythagoras was really the one that found this theorem or not, I might be able to throw some extra credit your way or not. Because I've always thought about it. I've never taken the time to actually look into it. So just a little bit of side stuff. Not trying to slam anybody or anything. But anyway, cultural appropriation and, that whole buzz of things being stolen, just trying to get to the bottom of the truth of whatever's been going on. But anyway, but for right now, we are going to say Pythagorean theorem. So what is the Pythagorean theorem? How does it go? Okay, so a squared plus b squared equals c squared. Okay, so then if we're going to solve here, walk me through it. What's our a? So we're going to say 5 squared. Our b, we're just going to leave it as b. And then what's our c? 13 squared. So then b squared is going to be equal to what? Okay, keep going.
25 plus 169.
Okay, not plus, but if we're going to solve for b, subtract the 25, right? So then we say 169 minus 25. So then b is going to be, now usually whenever we do square root, what symbol do we need to include? Okay, usually if we take square root on both sides, what symbol goes in front of the radical? Plus or minus, but because we're doing distance here, we're just going to take the plus, right? Usually when we do square root, it's plus or minus. For this purposes, we're just going to take the plus. Let me see, 169, 149, 144, right? So then 12, right? So then b is 12, okay? So then if this side is 12, so now we're ready to find the 6 trig functions. So now sine of theta is now going to be what? From SOHCAHTOA.
12 over 13.
So let's write it here. So and I feel like you all know this. I'm just doing this for instructional purposes. So sine is what again? So that's going to be what number?
12 over 13.
Okay, if that's sine, let's go ahead and do cosine of theta. And then tan of theta.
12 over 5.
Any questions here so far? All right, so if this is sine, again, what's the reciprocal of sine?
13 over 12.
Which trig function? Cosecant, right? So cosecant theta is going to be what again? 13 over 12. What's the reciprocal of cosine?
13 over 5.
Secant, right? Secant. It's okay. It's okay. We just starting, so. And then what's the reciprocal of tan? Cotan. And what is that going to be? Up. Oh. One moment, my good sir. 5 over 12. And then I want to try something really quickly. Can I do the following? Come on. Exit. Yes, I want to keep them. Yeah, shoot. Okay. So then what I want to do is, where is it? This one? Give me just a moment. I want to duplicate. Do I get the original? Oh, no. Oh, no. No. Oh, I duplicated the wrong one. Give me just a moment. I'm still kind of getting used to this. I want to duplicate this. That's what I want. And then this one, what I really want, yes, I want to get rid of that. Awesome. That's exactly what I want. Boom. And then this one, we can start it back. And then I should be able to, right here. And, oh, darn it. Let's see if this, and I can't erase it either. I was almost there. I didn't mean for it to come out that way. Let me try one other thing really quickly. Well, we have that slide. I was going to clear it out, but I think I know what I'll do next time. I have a plan for that. Okay. Anyway, it has to kind of be like this for right now. Yeah, okay. Actually, yeah, I'm not going to worry about it. Okay, there were a few questions. Go ahead. Let's go ladies first. Okay, so okay, the hypotenuse. Okay. So with right triangles, right, the hypotenuse is always opposite the largest side. So it's going to be opposite the 90-degree angle. But the hypotenuse is opposite the largest angle. That's yeah. So then that's the first thing. You want to identify the longest side. And then you usually have two other short legs, right? So since our theta is in the bottom left, for instance, is the 5 opposite the angle theta or is it next to the angle theta? It's next to it because it's touching the angle theta, right? So the opposite of angle theta is the leg that's not touching. Does that make sense? The angle. So then once you identify opposite, then adjacent is the one that's touching it, and hypotenuse is always the longest side. And that's a valid question because we do have to be clear about the orientation. I know that sometimes it throws students for a loop. Does that make sense? So once we identify the opposite and adjacent hypotenuse, then we can quickly find sine, we can find cosine, and then once you have sine and cosine, the rest just kind of flow from there. Okay, Mr. Hightower.
Our answer as a fraction of 12 over 13. If it's possible to reduce.
Yeah, we always reduce fractions whenever possible. I think I know how to work it properly. So I've never really taken notes directly in a PowerPoint, but I think I know how to do it so that it displays properly at the end. So I can't fix this one for right now, but going forward, I think I know what to do. Okay, any other questions? Let me see really quickly. So we did all that stuff. Let's confirm we did that. We got the 12, so that's good. And I just want to confirm our numbers, and our numbers look good. Okay, any questions about this before we go forward? Okay. All right. So moving along. So now that was, I forget the objective, but that was the some trig identities. Mm, yeah. So let's move into some fundamental identities. Let's look at this. So I think we talked about this already. The reciprocal of sine is cosecant, reciprocal of cosine is secant, and reciprocal of tan is cotan. Also, tan is sine over cosine, right? So that's what tan is. Is that okay with everyone? So tan is not only is it opposite over adjacent, but another way of expressing tan is sine over cosine. If we go back to the examples that we did, and we did sine over cosine, then we'll get the same result. Okay? And then cotan is the reciprocal of that. All right. So given this sine and given this cosine, we're asked to find the value of the 4 remaining trig functions of theta. Okay. So now with this one, let me try my technique again. So what I'm going to do is exit out, and we are on slide 13. So I'm going to get a copy. I'm going to duplicate it, and I'm going to let that be there, and this is the one that I want to work on. So this was my plan that I was thinking about. Okay. Let me do one other thing. Slide 13, this one. Let me get rid of all of this stuff. Boom. Yeah, we can get rid of that too. Yeah, we can leave that. Let's get rid of it. Okay, cool. So now I have a copy of the original without the annotations, and so now we have space to draw. Okay, so given this sine and given this cosine, so we have our sine. I typically just kind of like to write the whole thing anyway. What color are you feeling? Orange. All right, so brace yourself. Hold on to your seats, buckle your seatbelts. It's time for a PJ. How does it go? It's a really bad joke. It's a really bad joke, so I'm giving you a fair warning. Knock, knock. Banana. Knock, knock. You know this one? Knock, knock. Knock, knock. Banana. Knock, knock.
I'm low.
Keep going. Just come on, quick.
Oh, who's there?
Banana.
Banana.
Knock, knock. Orange. Aren't you glad I didn't say banana? Okay. Okay. All right, bad joke. I had to. I couldn't resist. I said, brace yourself. Hold on to your seats. It's time for a PJ, a poor joke. Go ahead. Huh?
Why can't you hear a pterodactyl once it's back?
Because the P is silent.
That was funny. That was funny. I wasn't gonna get that one. I was like, because their wings are silent, they fly like I was like, I was going. That was a good one. That was a good one. Okay. All right. So let's get back on task. This is enough for the PJs. I feel like somebody can make a song out of that, like just a whole song, like a rap or something, out of nothing but poor jokes. But I feel like that's what Weird Al Yankovic does. But his stuff actually be making me laugh sometimes. I like it. You know Weird Al Yankovic? He will take like the popular songs and do like parodies on them. So like Michael Jackson Beat It, and he did a bunch of stuff. And so it's just fun stuff, just being silly. Okay. So now, given these 2 trig functions, so now if we have sine and cosine, which one could we quickly? So I heard orange, right? So which one could we quickly go ahead and find if we have sine and cosine? Tan, right? So then tan of theta, what was tan again? So we just said that tan is sine of theta over cosine theta. So in this case, that's going to be what over what?
It's going to be radical 10.
Divided by?
Over 10.
Divided by?
Divided by 3 radical 10.
Okay. So when we say a fraction divided by another fraction, what do? What's the technique? Keep
the denominator. Right?
Keep change, flip, right? So whenever we say a fraction divided by another fraction, we do keep, change, flip, okay? So then we would keep the first one, so we're going to leave this like this, change division to multiplication, and then flip the second one. So the second one's going to become 3 root 10 under 10, right? So now given something like this, what do you notice or what happens? We got a lot of cancellations going on, right? So what cancels? These 10s cancel. What else? The radical 10s cancel. Okay, so now after these cancellations, what are we left with? What's left on top? 1. What's left on bottom? 3, right? So tan of theta should just be 1 over 3. Is this okay with everyone?
Yeah.
Okay. All right, so if this is tan, now where do we want to go next? Yeah, reciprocal functions, right? So then what's the reciprocal of sine? Cosecant, right? So then what is cosecant going to be? Okay. So we could probably leave it as 10. Now, usually we don't leave radicals in the denominator. Let's go ahead and rationalize this. So if we're going to rationalize, which means we're going to get rid of the radical in the denominator, we're going to multiply the top and the bottom by... Yeah. What you said first was, yeah. We're going to multiply by 1 in the following form. Root 10 over root 10, right? So now we get the power of 2 like we want. So we'll have... So the top is going to be 10 times the square root of 10 divided by what number? What's the square root of 10 squared? So, yeah. In case you don't see this, this means the same thing. So if we have root 10 times root 10, that's the same as the square root of 100. What's the square root of 100? 10, right? So 10 root 10 over 10, what happens? These cancel, and the final result?
301.
Just root 10, right? I know you were looking at the one above. Is that okay with everyone?
Yeah.
Okay. So cosecant theta in this case should just be root 10. So then if we can do cosecant, what's the next one? Secant theta. Where secant is the reciprocal of cosine. So that's going to be 3 root 10 under 10. Okay. Again, we need to do what again? Begins with an R, what we just did. So we need to rationalize by multiplying by 1 in the following form, root 10 over root 10. Okay. So then we get on top, we get 10 root 10. On bottom, we get 3 root 100. Same kind of deal as before. Root 100 is 10. So then we get 3 times 10. What happens with those 10s again? They cancel. And we are left with square root of 10 over 3. Okay, so we got this for tan. We got this for cosecant. We got this for secant. What's the final one? Cotan theta. What's cotan? The reciprocal of tan. So this is just going to be 1 over 3, which is just... Is that okay with everyone? So these should be the 4 remaining. Let's see, how did we do? So based on the quotient, tan, they got a third. I think we got the third, right? Okay. So we got the third. Cosecant is 1 over sine. We rationalize, just square root of 10, we got that. 1 over cosine, I think we got root 10 over 3, and then this one was just 3. Okay. Any questions here? Questions, comments, or concerns? Okay. Moving along. I'm starting to get into my rhythm and flow with these now. I'm starting to get the hang of it. So now we have some Pythagorean identities, okay? So the main one, honestly, this is actually just one identity, just expressed different ways. So this is really just the Pythagorean theorem, sine squared plus cosine squared equals 1. Right? That's the main one. Does anybody see, or anybody have a way for us to go, given equation 5, how could we produce equation 6? Given equation 5, how can we produce equation 6? How can we transform equation 5 into equation 6? Okay. I want to keep... I want to duplicate this, and let's go back here, and let's start the party back. Okay, well, did I duplicate the wrong one? I keep doing that. Give me just a moment. I duplicated the wrong one, I think. Yeah, I duplicated the wrong one I didn't intend to duplicate. Let me get rid of this, and I want to duplicate this, and let's go back here. Okay. What color are you feeling? Okay. So now, given equation 5, how can we, what manipulation could we do in order to transform it into equation 6? Mm-mm.
I thought sin and cosine would be tan, which would give you the tan out.
Okay, what's the relation between sine and tan? What is tan? What did we just say that tangent is?
Sine over cosine.
So sine over cosine, right? So if we have sine and we want to transform it to tan, if we divide every term or the left side and the right side by cosine, we can transform it into tan. So what I mean by that is the following. If we want to transform it into tan, we would say, let's use a different color. Clear the ink. Let's use something that's a little bit brighter.
Use red.
So if we divide by cosine squared theta, cosine squared theta and cosine squared theta, notice we get this. Does that make sense?
Yes.
Because sine over cosine is tan. Something divided by itself is 1. The reciprocal of cosine is secant. Okay. So if you locked in equation 5 with that orange manipulation, you automatically get equation 6 when you need it. Does that make sense? So can we do something similar for equation 7?
Secant over tan. I mean, divide everything by secant.
Not by secant, divide everything by.
By tan.
Uh-uh.
By 1.
Mm-mm.
By secant.
What'd you say? Not cosine. We've already did cosine.
I said secant.
Oh my goodness.
It's not secant.
Sine. Let's see what happens when we divide everything by sine. If we have sine and we have cosine, how do we get cotan? Cotan is what? Right? So it's cosine over sine, right? Okay, so I want to keep, that's fine. I want to duplicate this and start the party back. Okay. So, given the original, I probably use red since it's a little bit brighter. Given the original, say we want to generate cotan. Cotan is the reciprocal of tan. In other words, cotan is also cosine over sine. If tangent is sine over cosine, cotangent is cosine over sine, right? So what I mean by that is if we divide everything by sine squared theta, sine squared theta, sine squared theta, sine divided by sine is 1. Cosine over sine is
Is it secant?
cosine over sine is cotan, right?
It is.
That's cotangent, right? And then 1 over sine, the reciprocal of sine is cosecant. Cosecant. You see it? So I think we have a copy of everything. Let's back up. See? So So here's the original. Which one again?
Cosine divided by sine.
Is yes. Why is that? What do you mean? So remember we said tan is sine over cosine, right? So when we go to find cotan and we take the reciprocal, so another way of expressing cotan is cosine over sine. All right? So we've talked about pretty much two or three different ways of expressing tan, right? In the right triangle trigonometry, tan is opposite over adjacent. Another way of expressing tan is sine over cosine. All right, so I'm just not writing it out. Let me see right here. All right, so tan is sine over cosine. Cotan is the reciprocal. So that's all we did. We were just playing on that. You see it? No. Don't. You're making it worse, right? Tangent is sine over cosine. Just at the top of the screen. Tangent is sine over cosine. So when we go to find cotangent and we take the reciprocal, it's just cosine over sine. That's it. All right? So that's why I keep saying, like, once we have sine and cosine, then the rest kind of flows naturally. All right? So that's what we were playing on here. So here's the original. When we wanted tan is sine over cosine. So we divided everything by cosine, which you see here. Right? We divided everything by cosine. We were able to generate tan. If we go back to the original and we want cotangent, cotangent is cosine over sine. So we divided everything by sine, and it gave us this. Does that make sense? Yeah. So really, all you really got to know is equation 5, sine squared plus cosine squared equals 1. And then if you need tan or cotan, you just have to do your appropriate division. All right, okay, so let's give it a go. So then we have the fundamental identities here. Tan, again, is sine over cosine. Cotan is the reciprocal. We just flip it. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine, so on and so on. So notice we have two expressions for cotan. You can either look at cotan as cosine over sine, or you can look at cotan as 1 over tan. It just depends on the case, so depending on whatever it is you need. Does that make sense? Is this okay? Yeah. Okay. And then the other one is the trig identity, sine squared plus cosine squared equals 1. But again, you just kind of have to flow. I don't know what that is. Oh, Pearson? I don't know. I ain't gonna worry about it. Okay. So, but yeah, we'll get these. We'll see these in action. Let's get some practice. Okay, so we're asked to find the exact values of each expression. Do not use a calculator. Okay, let me do this. I want to keep my stuff. Duplicate. You can put these in the calculator. I'm gonna delete. I can get rid of that too. Yeah, that can go. I don't need any of that. Okay. So let's get the party started back. Okay. Find the exact value of each expression. Do not use a calculator. So actually, yeah, if you have a graphing calculator or even a scientific, if you put it in the first one, if we put it in the degree mode, you can just type it in and it should spit out the answer. So you can use that to check, right? But make sure you're in the proper mode. And I'll do a demo on that momentarily. Find the exact value of each expression. Do not use a calculator. Let me think about this. Okay, we got it. What color are you feeling?
Red.
I don't think I have pink. So I'll do red. That's okay. So now we just said that sine over cosine is actually what? Tangent, right? So this is actually tan of 39 degrees minus tan of 39 degrees. So then what's the result there? 0. Something minus itself is 0. Okay. And then for part B, okay, so cosecant is what? The reciprocal of what? Sine, right? So this is actually the same as cosine squared pi over 4 plus cosecant we said is 1 over sine squared of pi over 4. And then that's all in the denominator. Is this okay so far? Yeah. So if we have a fraction divided by another fraction, what's the technique again? Keep, change, flip. So this is the same as cosine squared pi over 4 plus what? Sine squared pi over 4. Sine squared plus cosine squared equals, from the Pythagorean, sine squared theta plus cosine squared theta equals, from the trig identity.
Tan squared.
No. We just said the main one that we need to know from the Pythagorean identity. What's the Pythagorean identity? Not Pythagorean theorem, but the Pythagorean trig identity. We said what? Sine squared plus cosine squared equals 1, right? Right here we have, is cosine squared plus sine squared, is that the same as sine squared plus cosine squared?
Oh.
So then this should equal 1. All right, okay. So that's the trig identity. Sine squared plus cosine squared equals 1. Okay. All right, so let's see. We should be able to go forward and confirm. We got our 0 and we got our 1. See, we didn't need a calculator. Does that make sense? Mm-hmm. Okay, let's try another one. So the next objective that we want to look into is finding the values of remaining trig functions. Can somebody confirm that they can hear the audio on the stream? So like maybe, open up the YouTube and just make sure you can hear the audio. Because I didn't really confirm that it's working. It should be working, but I don't want to assume. So yeah, just open it up real quick and confirm you can hear the audio. Okay. So the next objective, we're going to find the values of the remaining trig functions given the value of one of them. Okay, let's see it in action. So given that sine of theta is a half and theta is an acute angle, find the exact value of each of the remaining 5 trig function values of theta. Keep the ink. I would like to, I think it's this one. Yeah. Okay, I'm going to duplicate this. I'm going to get rid of this section. Okay, I can hear it. Thanks.
He still got it.
Stop it, because it's picking up. No, I don't think it is. I don't know what it is, but I'm okay. Okay, so now we're given that sine of theta is a half and theta is an acute angle. Find the exact values of each of the remaining 5 trig functions. I think we can just use, let me look at something really quickly. The first uses the definition of trig functions. The second uses the fundamental identities. Let me think about it. It's less than 90. It's fine. I mean, I kind of want to just jump right into the right triangle trigonometry. Oh, okay, here we go. So now, we have that theta is an acute angle. So let's just use, I'm going to use a Pythagorean identity, right? They gave us sine, so we should be able to quickly find what? Give me a color. What color are you feeling? I think I heard blue. Okay. So let's use, so if sine, let me kind of see what was the first, how did they start it out? Okay, so they are using right triangle. Okay, that's fine. Let's just do that. I'm so confused. Hey, hang on a second. I'm just talking about my annotations. Keep, that's fine. I thought I deleted that. Did I not duplicate it? Oh, I'm writing on the wrong one. Oh, okay, I get it. Okay, let me just go back here. Okay. So I don't know. I can't get rid of that now, though. That sucks. Let me look at one other thing. Can I? Oh, I can. Oh, that's awesome. So I can go back and change the other one, too. Yay, I'm so happy. Okay. All right. I'm just getting used to working PowerPoint. Okay, so we're going to use, it's because theta is an acute angle, we can use right triangle trigonometry, right? Okay, so let's start off with the right triangle. I don't want that color, though. What color are we feeling?
I thought we were using blue.
Okay, we can use blue. And okay. So let's start off with the right triangle. So I'm just drawing, and this is our 90 degree, and it says that theta is an acute angle, right? So it says that sine of theta is 1 over 2. So then where does the 1 go? Where does the 2 go?
I put the 2 on the 1.
What does sine stand from SOHCAHTOA?
It's opposite over adjacent.
Opposite over
Adjacent.
so?
I mean, over hypotenuse. I'm sorry.
It's okay, it's okay. Opposite over hypotenuse, right? Is this okay?
Yeah.
So if this orientation is proper, what side are we missing? The what side?
The opposite.
Not
the
the adjacent side, right? How are we going to find that? Use what theorem again?
Pythagorean theorem.
Okay, oh no. Come back. Stop, come on. There we go. So we're going to use what? A squared plus B squared equals C squared, okay? So then what's our A? We're going to let that be our unknown. We're going to just let this be A. And just to be a little bit consistent, we're going to say A squared. Now what's our B? We're going to say 1 squared equals 2 squared, okay? So then A is going to be the square root, what is that? 4 minus 1, which is the square root of 3. Is that okay with everyone? Okay. So then A, again, is the square root of 3.
I got a question.
Go ahead.
Will the theta always be down there in that specific?
No, but when we're drawing it ourselves, we can essentially put it here for right now. But that's a no. It's not always going to be there. Huh? For right now, for these discussions, this orientation is fine. You'll start to see when it'll change. It'll just kind of come out. You'll notice it. All right? Okay. Okay, so now we have all the parts. It says find the exact value of the remaining trig functions. Okay. So then once we have all parts of the right triangle, we already said that sine of theta is a half. I think this is okay. So tell me about cosine of theta.
Oh, you're asking about the.
So from SOHCAHTOA, let's do SOHCAHTOA like
Sine
this.
is adjacent over hypotenuse.
So cosine is adjacent over hypotenuse, right? So then that's going to be the square root of 3 divided by 2. Tell me about tan of theta.
It's opposite over adjacent.
Okay, so what over what?
1 over 3 and
Square root of 3. But then if we rationalize, we'll finish with
1/3.
top and bottom by what number?
Oh, it would be 3 over radicand over 1, right? But it would just be radicand 3, right?
Top and bottom by what number? So we're going to multiply by 1 in the form of, if we're going to rationalize this to get rid of the square root of the denominator, we multiply the top and the bottom by the square root of 3. All right? So we're going to multiply by 1 in this form to rationalize.
Okay.
All right? Is this okay?
Yeah.
So then what it gives us, I'm going to kind of,
Give us 1, right?
we're going to get the square root of 3 over the square root of 9. You see why I'm choosing the square root of 3? Now we get a perfect square, right? So then we get the square root of 3 over 3. These go a lot faster. Once you work a few examples, it goes fast. Initially, it can be a little intimidating, but once you see it a few times, you'll be able to do it really quickly, right? So we got our tan of theta. So now we're ready for the what functions? It's okay. Reciprocal. That's okay. The reciprocal functions. Okay, what's the reciprocal of sine?
2 over 1, which would just be 2, right?
It's 2, but what's the trig function? Cosecant, right? Cosecant theta, and the answer is just 2 there. What's the reciprocal of cosine? Secant, right? Which is just going to be 2 over root 3. If we rationalize, can you tell me what's going to happen?
You're going to get 2.
Wait. We multiply the top and the bottom by what again?
It's going to be 6. It's going to be radicand 6 over radicand 9.
Top and same kind of deal. Top and bottom by square root of 3. Okay? So then if we do this, now we can only move them into the same radical if they have the same index. So we can't multiply the 2 and the 3 in this case.
Okay, so
If it were the square root of 2, if it were the square root of 2 times the square root of 3, then it would become the square root of 6. See what I'm saying? But because the square root is not there, we leave them separate. So then this becomes 2 times the square root of 3. Ultimately, it's just going to be 3 because the square root of 9 is 3. Is this okay so far?
yes.
Okay. So then I think we're missing one more. What's the last one? Cotangent theta. And that's just going to be the reciprocal of tangent. So I'm going to write it here, 1 over tan theta. What's that result going to be?
3 over. Wait, no, you got to multiply.
Yeah. So yeah, if you did 3 over root 3, then you have to rationalize by doing what?
It's going to be 3. It's going to be.
So what you're saying is correct, and you would have to write it and kind of follow the changes. Instead of flipping the last answer, go back to the first line for tan. If we flip that one, what result do we get?
3 over 3.
Yeah. So it's just the square root of 3. Is that okay? So we get this one, we got this, we got this, we got this, and we got this. It takes practice. Again, we could flip that last line for tangent, but then we're going to have 3 over root 3. We have to rationalize again, do our cancellations. Ultimately, we get back to this. Or if we look at that first line for tan, we have 1 over the square root of 3. If we flip that, then we just get the square root of 3. Does that make sense? So, but what you all were saying was correct. I'm just trying to help you to see how to simplify it. Okay, so we got these results. I'm watching the clock. Okay, we got about an hour and 10 minutes. Let's keep going. And we got 41 slides, which is okay. So I think we did that. Let me see. Because sine equals b over c, draw a right triangle with an acute angle theta opposite of 1 and the hypotenuse is 2. So we did that. The adjacent side A can be found by using Pythagorean theorem. We did that. So we got the square root of 3 for A. So then cosine, we use SOHCAHTOA basically for those, and then cotan. Okay, any questions? I think we got these same results. And don't try to do all this in your head. You should write it out. I know some of the confusions come because we're trying to do a lot of this in our head because some of it is quick. The best thing is just to write out each step. That way we minimize our confusion and our chances of making mistakes. Just write everything. Okay. So then the second option is by using the Pythagorean identity, right? So let me get a copy of this. This is slide 27. Keep. I want to duplicate this. This one, I want to get rid of this stuff. Delete, 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 and one more. Let's delete. Okay, let's get the party started back. So now, let's see how we can do this. We can solve the same thing, but using the Pythagorean identity, okay? What color you feeling?
Red. I was going to say yellow, but it's red.
Okay, we can do red. All right. Okay. So how does the trig identity go? We said earlier that what? Sine squared what? Keep going. Sine squared plus cosine squared theta equals 1, right? Okay. So now earlier we said that what sine squared was what, a half? Was it sine squared or sine? No, it's sine of theta is a half. So if sine of theta is a half, wait, you gotta wait for, we're missing someone, you gotta wait for them to come back. I can't have more than one person out at a time. So if sine of theta is a half, that means we can do 1/2 squared plus cosine, oh, did I clear? Shoot, I think I did click that button, okay. Did I undo? Oh, I think that works here. I'm sorry, I'm still, so, Apple has done a lot of updates and I'm still getting used to the updates because I think I just realized that I can, nope, that doesn't work, 3 fingers. No? Maybe not. I don't know how I cleared that. Can I double tap? No? Whatever. Let me just erase and go like this. Okay. And go like that. Okay. So cosine squared theta equals 1, right? Yes. So we can solve for what?
If we put,
What trig identity, what trig function don't we know? Tan. No. So we plugged in sine. We can solve for cosine, right? So if we're solving for cosine, we got cosine squared theta equals what? 1 minus 1 over 4? Mm-hmm. So then cosine of theta is going to be, what's that? 4 over 4 minus 1 is 3 over 4. So we would say the square root of 3 over 4, right? Again, this is the same as the square root of 3 over the square root of 4. Square root of 4 is 2. So this should be the square root of 3 divided by 2. Is that what we got before? Yeah. So now we have, so let's kind of put it all together. Okay, you all can switch out. Thank you. So we said sine of theta is a half. Cosine of theta, we just said, was the square root of 3 over 2. So that means that tan of theta, again, as a recall, tan is what over what again? Okay, so tan is sine theta over cosine theta. So that's going to be a half over the root 3 over 2. Ultimately, you get 1 over root 3, which is going to be root 3 over 3. I kind of skipped some steps there. Is that okay, though? But you should be able to, once you get this set up, you should be able to crunch it down to here. Okay? So then if we have these, what's the reciprocal of sine? Which identity? Which trig? Cosecant. It's okay. Cosecant theta, so what's that going to be? 2 over 1. What's the reciprocal of cosine? Secant.
See, I gotta go home.
It's okay. Secant. That's going to be 2 over root 3, which becomes 2 root 3 over 3. Okay, I think we got that. And then cotan theta. So it's just going to be this one, right? It's a reciprocal. Remember, we just flip the result. The reciprocals, we just flip the previous answers. And I think we got all those results before, right? So we saw 2 different ways of solving that. Okay. So I think that's what this is going to talk about. So then root 3 over 2, we got that. 10, I think we got that. We got all that stuff. Any questions about any of this before we go forward? Okay. Watching the clock. We still got some time. Okay. All right, let's keep it going. Finding the values of the trig functions when one is known. Given the value of one trig function of an acute angle theta, the exact value of each of the remaining 5 trig functions of theta can be found in either of 2 ways. Didn't we just do this? Oh, draw a right triangle showing the acute angle theta, or 2 of the sides can be assigned values based on the value of the given trig function, and then find the length, use the Pythagorean theorem, and then use the definition in equation 1 to find the values of the remaining trig functions. So that was like the first way we did, where we drew the right triangle and solved it based on that. Another option was to use the appropriate, it should be a Pythagorean identity, or a trig functions. Okay? Yeah, that was the second version that we did, right? All right. So given that tan is 2/3, theta is an acute angle, find the exact value of each of the following, of the remaining 5 trig functions. Do we want to see the right triangle version or the trig identity version?
The right triangle.
Okay, we'll do the right triangle, right? So first, let me get a copy of this. Let's keep. We want to duplicate that slide, so let's duplicate. Yeah, so let's go here, and we want to clear out all this stuff. Delete. We said right triangle, so I'm going to, I was going to leave it, but, I mean, I still could, actually. If I just change this text, just delete that. Okay. Oh, no. Then I want to delete that, and we'll keep this. And actually, what I'm going to do, I'm going to duplicate it at this point. So that way here, I can delete that. Boom. And we'll start here. Okay, so since the request was for right triangle trigonometry, we should be, here it is, right here. Okay. So given that tan is this, I'd rather start from scratch, actually. Okay, I think this is the one. What color are you feeling?
Black.
Okay, yeah, because we definitely have not done black. Okay, so we have that tan of theta equals 2/3, and it says that theta is an acute angle, which means that it's less than 90. So if we start with a beautiful right triangle as such, we put our theta here, all right? So tan, 3, all right? So given this, we can find the what? Hypotenuse. This is probably inappropriate. You all watch Key and Peele when they were out? Key and Peele? So they had a joke. There was a substitute teacher, and he was trying to talk about like Pythagorean theorem. He was like, we have Pythagorean theorem is the sum of the squares of the legs is going to be the square of the hypotenuse. And then one of the students was like, I'm always high on hypotenuse. You know, so every time I hear hypotenuse, I always think of that skit with Key and Peele. He's talking about being high on hypotenuse. Anyway, they're just silly. Okay. Ooh. Okay, so how are we going to find this hypotenuse? That's going to be our C. How are we going to find that? What's the Pythagorean theorem again? Okay. So one of my mentors would say things like, every time you use a formula, write it down, and that helps to ingrain it in our memory. So then let's apply. Okay. What's our A? That's fine. I'm going to do 3, though. What?
Does it matter which one is A?
Just as long as you have the short legs, right? Some of the squares are the short legs. So 3 squared plus 2 squared should be C squared, right? So then C should be the square root of, what is that, 9 plus 4?
Yeah.
So square root of 13. So this should be the square root of 13. Okay, this is looking good. So given that tan is this, find the exact value of the remaining trig functions. Okay, so let's just go down the list. So tell me about sine of theta.
It's gonna be 2/13.
2 over root 13. If we rationalize, can you tell me the final result? Do I need to?
It's gonna be 2 radical 13 over 13.
Awesome sauce.
Shit.
Everybody okay with that? Any questions there? Is it clear where that answer came from? Do I need to show where that came from? Okay. So then what's cosine of theta? Tell me about cosine.
Adjacent over hypotenuse, so it's 3 over root 13.
And then the final result's going to be?
3 root 13 over 13.
You see, I told you, once you see it a few times, it goes quickly.
I'm starting to get it.
Okay? She gets revving me up now. She's excited. I'm getting excited. Yeah, like that's awesome though, right? But you see it. Okay. That's what I'm here for to see those sparks going off in people's minds. Go away, please. Thank you. Okay. So I don't know if I told you all this, but I'm a technology whisperer. You know what I mean by that? You ever notice like when you're by yourself and like you're doing stuff and it works, but then you go to show somebody and it just start messing up? And so it's like I've noticed that with the technology, as long as I kind of be kind to it, it'll work. But if I start saying stuff like, "Oh, stupid calculator" or "stupid computer," then it start acting up and it starts showing out and it start like shutting down for no reason. So I consider myself a technology whisperer. One day I'm going to be, I'll be like hacking people's phones. Let me see if I can get it to work. Hey Siri, call mom.
Oh, wait a minute. Mine ain't gonna work because I got found out.
Calling Carolyn.
Mine is working. Oh, I gotta stop it. But I would hack Suda's phone. Sometimes I walk around and I just say, "Hey, SIRI, call mom," and then their phones will be like, "Stop making my phone work." You can use people's phone if they have their Hey Siri on, and like sometimes it'll work. Anyway. Okay, so we got sine and cosine. What's next? All right, tell me about tan of theta.
2 over 3.
Tan opposite over adjacent, 2 over 3. Okay. Tell me about some reciprocal functions.
3 over 2.
Wait, what's the first one?
Wait, what do you mean what's the first?
Okay, what's the reciprocal of sine?
It's secant.
Secant? No, not secant. Cosecant, right?
Secant is the second one.
Remember, it's kind of backwards, right? So the reciprocal of sine is cosecant. I'm going to write it over here, though, because I'm about out of space. So cosecant theta, it's just the properties. Secant, it's like when we start looking at the graph, you'll see why these things match up. Yeah, I don't know why they named it like that. 'Cause you're right. It seems like they could have just easily shifted the name, But it's like sine and cosine, they're called cofunction properties. So the sine and cosine happens that way because one graph is the other graph shifted by 90 degrees. And it's a similar discussion for secant and cosecant and then tan and cotan. I don't know why they named it the way that they did, but as far as the cofunction properties, that's where that comes from. So now tell me about cosecant. Cosecant is the reciprocal of sine. Cosecant is the reciprocal of sine. So then that result is going to be what? Right? If we flip the original, that's going to be the square root of 13 over 2. I'm just going to continue kind of going to the side. What's after cosecant? Reciprocal of cosine is secant, okay? Secant theta. And that's going to be what in this case? Radical 13 over 3. And then the last one is cotangent is the reciprocal of, and that's going to be, in this case, 3 over 2. So we got this result, we got this result, we got this result, we got this one, and this one. Any questions here? Okay, let's see how do we do. So we use the right triangle. That's going to kind of overlay on top of our stuff. Okay, that's not too bad, actually. Let me do something really quickly. Keep, that's fine. I'm not worried about that. This one, I want to get rid of, yeah, we don't actually need that. Deletes. Awesome sauce. Okay, I can make that other change later. So we did this. We used the right triangle trigonometry, and we did all that. I think we got these results. Okay, any questions here? I think they got the same things that we did. Any questions here? Wait, did we make a mistake? Oh, we got the 3 root 13 over 13? Okay. All right, I think we did all that. Okay. So next objective, we want to look at some examples on using the complementary angle theorem. Complementary angle theorems. Let's see. Do I want to use this? Sine of B. Okay. So if we look at this, right? The sine of angle B, sine is what? Opposite over adjacent. So that was what? B over A. And so the sine of angle B is actually the same as the cosine of angle A. You see the difference between angle B and angle A? If we look at this, right?
Oh, yeah.
If we say, oh, it's a little quirky. If we say the sine of angle B, that's going to be little b over little a. The sine of angle B is the same as the cosine of angle A. That's the what is it called? Complementary angle theorem. So two angles that add up to 90. So again, the sine of angle B is the same as the cosine of angle A. Is this okay? And then the rest should flow naturally. So sine of angle B is the same as cosine of A. Cosine of B is the same as sine of A. Tan of angle B is the same as cotan of A. Is this okay? I feel like Dr. Seuss. Because of the rhyming. Okay, I'm going to let that be, right? Is this okay before I go forward?
Yes.
You could take a picture. And keep in mind, this is already on Moodle. If you want to take a picture, you can. Did you take a picture? You're okay? I mean, you could take a picture. I don't mind pictures. Like, so that way. I mean, you could like picture and then keep writing. So that way we don't have to stop. No? Okay. I can't think of anything else here. Okay. And again, all this stuff is actually already on Moodle. So what is recommended is that we pull up our notes before class and look at the notes ahead of time. That way when we get in class, hopefully it can be a review, idealistically, right? Okay, what are we looking like? We are moving way slower than I would like, but that is okay. I like this rhythm. So complementary angle theorem, cofunctions of complementary angles are equal. So that's basically what you just saw us do in the last one, in the last example, okay? Okay, so sine of theta is the same as cosine of 90 minus that angle, okay? So this is the cofunction property. So sine goes with cosine. Sine and cosine go together because one is the other shifted by 90 degrees, all right? Cosine is sine of 90 minus theta, so on and so on. So 90 degrees is the same as how many radians? Or what's 90 degrees in radians? How do we convert 90 degrees to radians? You said pool water? Like chlorine? I don't know. How do we convert 90 degrees to Okay, let's do this conversion really quickly. What color are we feeling? I wish we could. It doesn't. I don't see how to do that here. So it's just something on the top. What color? What color would you want to make?
Maybe like darker blue.
A dark blue, so we'll just do blue. That's the best we can do right now with this system. So let's convert, right? Say we have 90 degrees. We want to convert to radians, right? We're going to say times. What's the conversion from degrees to radians? Pi over 180, right? Since we have degrees on top, when we do the conversions, we need to make sure that degrees are on bottom. So now the units of degrees cancel, and we're left with radians. Remember, we did this before, right? Right?
Wait.
It was the first.
Before this?
Yeah. Right? So then 90 divided by 180 is what? Or what happens?
It's 16,000.
Divide. 90 divided by 180.
Divided by
2, right? 180 divided by 90 is 2. So this is going to be pi over 2. You see it?
Yeah.
So 90 degrees. And then, so let's do the reverse really quickly. Let's do this color. Say we have pi over 2 radians, and we want to convert to degrees. So if we have radians on top, when we do the conversion, how do we convert this to degrees? Times what? Keep going. 180 over pi, right? So we would say times 180 degrees over pi radians. Again, the units of go like this.
Pi cancel out.
Yeah, the units of radians or whatever are going to cancel. So then 180 divided by 2 is,
90.
all right. Okay, so just as a quick little refresher, converting from degrees to radians and vice versa. Oh, okay. Well, okay. So I'm going to let that be. Do they want us to find the exact? Oh, that's all they wanted? Okay, that's what I thought. I was like, yeah, I was like, I didn't see it beyond that. Okay, so if we use the complementary angle theorem, sine of 79 degrees is the same as cosine of 90 minus that angle, right? So then the result there was cosine of 11 degrees. So then using that same technique, let me do this. Let's duplicate. Awesome. That's exactly what I want to go. Awesome. Awesome. And awesome. Okay. So again, using still getting used to the controls here. Okay. Complementary angle theorem. Again, this is the same as cosine of 90 minus 79. So this is going to be, what is that? Cosine of 11 degrees. And then we just leave it there. Then, can we see the next? There it is. So tan of pi over 18 is the same as what? Cotan of what? So it's going to be what? Pi over 2 minus pi over 18. That's going to be cotan of 9 minus 1 is 8. 8 pi over 18, which becomes cotan divided by what? 2. 4 pi over 9. So basically we said pi over 2 minus pi over 18 to get 4 pi over 9. You can use your calculator to quickly crunch these, you know. Walk me through this one. Cosine of pi over 3 is the same as what? Sine of...
Is it 90?
The 90, what's 90 in radians?
It's pi over 180. No, whoa. Back that up.
Okay, it's okay. Pi over 2 minus pi over 3, right? So let me see something. Hey Siri, what's 1/2 minus 1/3 as a fraction?
1 over 2 minus 1 over 3 is about 0.1666.
She didn't give me the result as a fraction. But you know, your calculators can do this as a fraction. So I'm just going to do it by hand here. Common denominator is what, 6? So then we could say 3 pi over 6 minus 2 pi over 6 to give us pi over 6. We might be able to take that one further, but just to keep the pattern, I'm going to keep going like this. And then what's this one going to be? What's the complementary angle? Or not yet. So if cosine goes with sine, if tan goes with cotan, then cosecant should go with secant, right? So this should be secant of pi over 2 minus 5 pi over 12, right? 12, so that's going to be so it's going to be secant 6 pi over 12 minus 5 pi over 12 to give us what? Any questions here? Well, I mean, but part of the challenge is you're trying to follow my work. I'm just showing you, I'm just kind of introducing the idea to you. Your job is to kind of take it home and figure out how to get it to work for you. And once you work a few examples, you'll see it. It's just like the other stuff. the earlier statement where you'll pick up on it after a few repetitions. Okay, there was another question I think I kind of didn't get a chance to get out.
I think I'm still just like
Processing a bit. Okay. So I think this stuff is okay. So let's see, how do we do? Cosine of 11, I think we got the 4 pi over 9,
so like
pi over 6.
do we get like some information from like that previous slide and like number
You talking about from this?
no before that.
From this? Yeah, this is what we've been using the whole while. So these are the complement using the cofunction properties and complementary angle theorem. Well, yeah, I'm just doing it because it says using the complementary angle theorem. So they just wanted us to directly use that theorem. Okay, let's get past all this. Okay. So find the exact values of each expression. Do not use a calculator. All right. Okay. Can anybody walk me through this one?
Oh, Jesus.
So if we use the same theorem, right? No calculator. Okay, secant of 11 degrees should be the same as what? So it should be the same as, I wrote the wrong thing. Probably. That's what it's looking like. So secant of 11 is the same as cosecant of 90 degrees minus 11 degrees. Then we're still going to bring this other thing down. 90 minus 11 is what? 79. And what does that equal? Okay. If we use the same property here, sine of 37 degrees, what's cosine of 53? That's the same as what? If we use the same, same little, so we transform the secant. What do we do with the secant? It's going to be 90 minus, so cosine is the same as what? Cosine is the same as what? Sine of 90 minus what? Yeah, 53, right? So then this is going to be sine of this. What's 90 minus 53? 37. Is this okay? You can check this with your calculator. It's not always going to be zeros and ones, but you know. Cosine. So cosine is sine of 90 minus 53. Right, sine and cosine go together, yes. Yeah, that's the complementary angle theorem. So sine is cosine of 90 minus theta and vice versa. Secant is secant of 90 minus theta and vice versa. Yes. 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 Is it okay? That's like he's saying, like you just got to keep working it and you'll see it. You will see it. I was like, you're doing Tai Chi? It's like, I'll just mess with you. Okay, what's the time? Let me see. The time. Okay, we got about 40 minutes. Let's keep it going. Oh, that was it. That was the last slide. Oh, okay. So up. Wait a minute. Yeah, let's keep it for now. Did I not duplicate that one? Oh, I just wrote on the wrong slide. So can I just like move these around like that and then get rid of like this? Yeah, I don't need that. I don't need that. I don't need this. I don't really need that. This looks better. Let's see, how do we do? Much better. And then we did all that stuff, right? We got all these, right? Oh, that was this previous slide. Did I? Wait a minute. Did I delete something wrong? I think I just deleted the wrong thing. Okay. This needs to be, let me just undo. Okay. Then I need to duplicate this. That's what I was missing. All right. And then this one, I can get rid of all this stuff. Awesome sauce. Nope, nope, nope. Okay, that looks better. I think we're back in business now. So I think we did all that. Let's get rid of all this. We did this. We got 0 and 1. Okay, and then on that slide, let me get rid of all these annotations, delete, and I think we're golden. Zero and 1. Okay, and I think that's the last slide. Okay. So, any questions from this section? So this was an example. We were exploring examples on right triangle trigonometry. Let's see how much time we have remaining. So 40 minutes. We actually kind of need to move on into the next section. We'll go ahead and start the next section. We got like, because we stopped at what, 10:50? So we still got like a good 40 minutes. So we need to take advantage of that. Any questions before I go forward? Okay, I'm going to stop the stream.